University of Mexico. He will talk about the spiral rings and arcs around the velvet star, and the introduction of Jesus will be made by
Thank you very much. He got his master degree in Korea, dentro de la astronomía y astrofísica en Seminario. Under the supervision of James Arthur. 2010, in 2012 he joined the CSIC grants for getting her PhD here. 2011. So 11, okay. So he got the PhD 3 years later, yeah, 3 years and a couple of months. And so it was a very fast track that he was doing at that time. He's very, very active, very productive. And after a few months here as a postdoc, he moved to ASIA, the Taiwan Astronomical Institute, where he was working under the supervision of the director of the institute, Professor Yowashu, for about one year and a half. He's been working all the time with both joining simulations, hydrodynamical simulation, with X-ray observation at the very beginning, and then he discovered the full spectral range, and now he is like multi-band astronomer. After 1 year and a half there in Taiwan, he was offered a permanent position in, now it was IAA, it was the same center as where he was with a master's degree, but now it's Instituto de Radioastronomía y Astrofísica. Okay. So now it's really a pleasure for me to receive here Jesus, investigador, profesor de investigación there in Andalucía, and he's been talking about a project that we have been developing for some time about the spirals and rings and arcs, some features that are produced in the very late phases of the stellar evolution and the very particular circumstances. So it's your turn. Thank you.
So thank you all for seeing talk. Again, I'm very happy to be back in Granada. I come back every time I can. I like tapas and I like visiting the institute, and of course my interaction with Martin is always very productive. So this is a relatively old project that Martin and Gerardo have been working in the past years, and I just recently joined them. And now the list of people working in this project is growing and growing, including Laurent Savan in UNAM, Luis Zapata, Bruce Balik in the USA, Alfonso Trejo in Taiwan, Hyosun Kim, a former co-worker in Taiwan too, and a summer student that we had when I was a postdoc in Taiwan. So what I want to talk to you is about these rings and arcs, and so I also want to say that, so normally, because here there's a very productive group about star formation, and you normally see these rings and arcs and things around star forming regions and stars that are forming, so that's why I wanted to place this last name. So I want to show you images and what we have been doing lately about different optical, infrared, and submillimeter observations. So this is an image of AGB star, U-Ant, with ALMA and the CO molecule. So you see this is different colors at different velocity bands. So you see a whole structure of something that is expanding and interacting with the interstellar medium. So this is very roundish. This is what we won't see in our sample. So first of all, I want to tell you a little bit about the institute. Most of you, or a few people here, already work with people in Morelia. So we are a very small institute. We're 25 professors, and we do different things, research lines. We recently, with different professors who have arrived, including me, we formed the Stellar Evolved Star Group. So we're just a group that is starting to grow. And we are in Morelia. Morelia is about 4 hours by bus from Mexico City, and it's a very nice colonial city founded by the conquerors. So my talk will be about So I will give a little bit of some details about the structural formation, what people think about these rings and arcs, the discoveries, how was this, all these discoveries were like building up on a theoretical structure, and then the project that we have been carrying out, some results, and finally I will end up with the remarks. So I want to start with, so if you don't know it, I'll tell you how this low mass stars evolve. So they start something with as a main sequence star, and then because of different processes in the outer layers, the star goes this way, and then it becomes a little bit red, and then it goes up to the AGB phase, where they become red and cooler red, and then they have, then at some point, because of carbon pockets and helium pockets near the core, the star becomes unstable and have this called so-called thermally pulsating AGB star. So at some point the star starts expanding this envelope, and it starts losing the material, most of these outer layers, into the interstellar medium. And then what we have is that the nude core evolves separately from this gas. So the core stays, and then the gas starts interacting with the interstellar medium. So then the star becomes an AGB, post-AGB stars, and then starts going down the cooling track of the white dwarfs. So this is a very, very general idea of how low mass stars evolve. It's very generalized, and then depending on the initial mass, the picture can change a little bit. So, but what happens to the medium around the star is, it's also, I can tell you first the cartoon, and then I'll show you some images. So the cartoon is that the star in the AGB phase, and it has very massive, dense, and slow wind. So what we have is that the star is surrounded by this dusty envelope of material, and it can last about 10 to the 5 years. So in this relatively long period of time, the star can lose up to 2 or 3 solar masses. And this wind is relatively slow, has a very slow velocity. So when the star becomes a post-AGB star, it becomes hotter, so it develops a fast wind. So this fast wind, which can be around 1,000 or 4,000 kilometers per second, shocks, compresses, and this AGB previously ejected material. And at the same time, the star develops a very high photoionizing flux. So what we have is that the star pushes away the material previously ejected, and then starts heating it up, and then we have a very nice planetary nebula, something like this. So this is the star. This is the most roundish planetary nebula that you will see, and it's not very common. So this is nature telling us that sometimes it could be, as we think, as simple as ideas. But then again, most of the AGB stars, they're not round. They have structure in it. For example, this is a very simple roundish material, AGB star, and then we have things like this, ripples. Probably the star is moving. It's a runaway star probably. Or something like this, like how can we explain this? And then planetary nebulae have like a diverse morphological features, from, again, roundish things to very complex structures around the stars. So this is a SO image where every planetary nebula here is scaled to different, so to their physical sizes. So you do not see it here, but there's one planetary nebula here. So there's very complex structures, some other here. So how do you go from something that is more or less roundish into something that is very crazy? Something must have happened between in this transition between the mature planetary nebula and the AGB phase. Something in between must have happened, probably the star, the ejection of material is not isotropical, it's binary, multiple systems in the core of these stars. So this is the cat-sized nebula. You can see it here, some structure here, and then some clumps this way. But if we do a close-up with the HST here, so we see that something that was probably more or less isotropic, or closely isotropic, currently the star have this bipolar, very, very bipolar ejection. So probably jets, you see, and they're actually jets that could be precessing because the jets do not have the same direction, but they're point symmetric, one can say. So we are interested, or mainly I am interested in this transition, from the AGB to the planetary nebula. So a little bit of story about these rings. Of course, you can see the rings here. This is the kind of rings, the kind of structures that I will tell you about. So in 1999, so this Mastrodemos and Morris, they wanted to do some simulations to reproduce this very bipolar planetary nebula. So they come up with the idea that it is probably because of a binary system. So a binary system, they thought that it could be able to shape the massless rate of the AGB star so that you will produce this very nice bipolar nebula. Most of the results are very isotropic, but for some orbital separations and orbital properties, they realized that spirals can be formed. So this is when we look at the plane, at the orbital plane, and this is edge on the orbital plane. So at the end, what you have is it's an AGB star losing material isotropically, and then a companion is revolving around it. So you see a nesting kind of shells, but it looks like a spiral if you look at from the top of the orbital plane. And they said that so far in 1999, they have never seen a structure like this, other than a galaxy, of course, in nebulae around low mass stars. So they said they defined this as an unknown type of hydrodynamic solution in which a spiral shock is formed, covering most of the solid angle around the binary. So that was 1999. And then Hubble was launched, if I'm wrong, 1994, probably, or 90s. So by 2000, these were the only 5 objects with these ring patterns. So far, no spiral, only rings. This is a carbon-rich AGB star. You probably don't see it properly, but there's like rings, broken rings. Also, these are 2 protoplanetary nebulae, and these are relatively mature planetary nebulae. So what we see is different. So it's the same ring-like structure in the different stages of evolution of similar stars. AGB stars, protoplanetary nebulae, and planetary nebulae. This was by 2000, and this was presented in a memories of a conference in 2000, so by these people. So they were just pointing at these 5 specific objects that Hubble has spotted these structures. By 2006, Mauron and Huygens, they observed a sample of AGB stars with a VLT and HST, and most of the images are very simple. They're relatively boring, kind of like this. It looks like it has some structure here, but who can tell? Or some fuzzy structure there. But then the surprise was this carbon star called AFGL I don't know if you remember, of course, you do. When I was a student, one of the first results of ALMA was the discovery of this spiral around an AGB star, which was some star that I don't...
Is this the same source that has been observed with...
No, it's another one. This was, I don't remember the name. R Sculptors. So they reported the discovery of this. This is, I think, CO emission from this AGB star. So they see, again, these are velocity maps. They estimated a period of 350 years for the, and a wind velocity of 15 kilometers per second, which is more or less what we expect for AGB stars. And they also have some simulations, and then they can, well, fit the dots here are, I think they're measurements from the observations, and they have the spiral thing. Here's the simulation. And I will present you. So this is a movie they did with the, so going like this, it shows different velocity maps, which is presented here. And they also did this 3D representation of the CO emission. So what we see is an outer shell interacted with the previously ejected material, and then kind of like a spiral shape. But as you can see, as soon as it leaves the star, it is clumpy, and probably some hydrodynamical instabilities are breaking the defined pattern of the spiral. Similarly, they did the same for the simulations. So they actually proposed that we are observing this structure because somehow the star, they catched it just after the star went into this high period of mass ejection. So previously, this is negative time. So when it reaches zero, it will be one of these major ejections. So if you see the material here, it's not very, the visibility is not very bright. Well, we have to wait 100 years. Maybe I can. No, I cannot. So, and then the stars will enter these thermal poles where the mass loss rate increases and probably the velocity does again. So the brightness increases. So the outer shell is explained as the interaction of the current material being interacting with the previously ejected AGB material. Again, the simulation is binary interaction, one just revolving around it. It's not that the star is losing mass with a dependence on time. It's the AGB star is losing mass at a certain rate, and then the companion star is just modulating the density gradient. And then now we can start rejecting some models. Now it is widely accepted that these structures are because of this binary interaction. So one can say, like, okay, whenever we see this spiral, it is because we have a binary in this nebula. And of course, after the ALMA results, some more people started investing some more time from the ground-based telescopes. In particular here, Cernicharo has some item 30 meters observations of these AGB stars, IRC 10 to 16. So they also report this amazing spiral structure. It's also the different velocity channels. And here I present these are CO and HC3 and emissivity maps from another AGB star from Hyosun Kim, performed with SMA in Hawaii. So also from ground-based telescopes, we were able to spot these spirals. But what are the implications of the planetary nebulae formation? As I said, is it true, or is it like one-to-one that if we see this structure, is it a binary or not? But then again, so Romano Corradi also in 2004 used the Isaac Newton telescope, right? And then he observed different planetary nebulae where he masked the stars in order to unveil the structures around this planetary nebulae. So what he did is he used the shift, divide, and add method, which is you take the image, the original image, and then you shift it a certain number of pixels, you add it, and then you divide it to the original. And then you do that for 4 different, like a box. So that enhances the very faint structures around the star. So you see these rings appear here, or some rings here. So this was very nice and very good job. But also these rings were unveiled by Spitzer. So we also see that these rings, this is a work by Gerardo. And, this is a very bad quality projection, but there are also some rings here. Actually, this image is way better by the computer. So we see that the rings can be seen in molecular emission, infrared emission, and optical emission, depending on the stage of evolution of the nebula, the central star. But then again, Ursula De Marco and some other people have been claiming that planetary nebulae can only be formed if the star is a binary or a multiple system. And they claim that it's between the 50 or 70% of stars that are multiple that form planetary nebulae. And Romano also suggested that these spiral rings and arcs should be present in all planetary nebulae. So what we want to do is we want to test these ideas. We want to know if it's true or not, or at least create some very nice images. So Gerardo, with his students and lots of people, they went into the HST and the Spitzer archives in order to search for these structures in AGB stars, protoplanetary nebulae, and planetary nebulae. And they performed the SDA algorithm in order to enhance. You can enhance some of the rings here. This is, you see the slit here is the representation of this cut here. So with this algorithm, you can unveil these structures. And then in this work, we reported 29 new detections. Okay, some of those examples are like this. So we see that these rings or structures are very faint in some of these very round planetary nebulae. So again, I'm showing you on the top is the color image, which can be HST or Spitzer. Then this is the SDA algorithm. And this is the cut. You see the slit here. So you see some of these rings are very faint and very close to the inner structures. And then some of them may look like broken. You see this is not a complete ring. So some of these are broken. There are some others where the nebula already evolved so much that you cannot follow them completely around the central region. Well, they're easily spotted here. See them up, down here. Some of them are spotted here. And in some others are very easy to see. So the problem with this is that some of these planetary nebulae are very compact, and sometimes we're fighting with the PSF or the instrumental response of the HST or Spitzer. So, but in general, there were 29 new detections plus 29 already reported sources. It makes 58 sources with any kind of ring structure or ring or arc or something. But there's a total of 700 sources already observed in total. So we can estimate very easily that the occurrence is around 8% of all planetary nebulae. So far, we can say that these structures are not common to any planetary nebulae. So we do not see any hint of spirals, but we see rings, arcs, so things that were already broken. But is it because they're not there since the beginning, or is it because they were destructed? They were there, but they were destructed by the different processes that create the planetary nebulae. For example, the stellar wind, the photons from the star, or any other physical process that you can think of. Then, after this very hard work, Sujins, this is a Korean student that I had when I was in Taiwan. She came to work for a summer, and she checked the 700 sources. She created a catalog, and she started searching for distances, magnitudes, morphological characteristics, everything of all the sources that we could find. So this is the whole statistic. So planetary nebulae are blue. This is distance from the sun, and this is the number of objects. So, of course, we are biased to the more closer objects, but we have a mix of all these, of the 3 stages of evolution. This is effective temperature. This is 1,000, 10,000, and 100,000. So, of course, planetary nebulae, these are the central star's effective temperature. So, of course, planetary nebulae are hotter than protoplanetary nebulae, and so on, than AGP stars. But we seem to have a very nice distribution of the 3 stages. And this is comparing the different dots, the different objects with the evolutionary sequence tracks from Miller-Bertolami. So what we see is, again, we see that these structures, something, they appear in all over the evolutionary sequence of these low mass stars. There is something here that is weird. So she also did some other comparisons, a lot of them, but it was a very, very nice job. And so she also measured, for those cases that we had the distances or between the rings, the separations between the rings. So here's again comparison between the effective temperature and, for example, the ring spacing in arcsec and in astronomical units. It may look like it's wider, the separation is larger than in those cases that protoplanetary nebulae. Simulations that I already presented about the spiral formation, it also suggests that this post-Orbis, the separation is a little bit larger, but I mean, you can see the statistics here is not very good, so it's not a very strong idea. So again, so we can, okay, let's say that these rings are there, they're always there, but why is it only 8% of these sources that we see? So there must be some mechanism destroying this spiral. So, or something is changing the properties of the structures around this of all stars. For example, something that I want to call your attention is that the ring here looks very well defined, and the ring on this side does not. It's very fuzzy. I can send you the image, but I mean, you can clearly see this ring, and this is not a nice ring. And so far, we only have this source that looks like a spiral. We only have one of those almost 60 sources. So the next step is we want to do detailed studies of some of the sources that have the best observations in order to characterize and to derive certain parameters from them. For example, so right now what we're doing is we are studying the brightest planetary nebula with the best observations from HST. So this is the same that I'll just show you. This is the Cat's Eyes Nebula. So you see very nice, the rings extending far beyond from the nebula. And you see the Saturn Nebula. So again, so this is the central region, and then the rings outside. They're very clear there. And then NGC 7027. You see the rings here, or arcs, are very messy. In this case, we more or less can say that the rings go the other side, but not in this case. So they seem to be broken or projected into different directions. And what I just said, just repeat it in your heads here. So you see some of the rings up here, there's something here fuzzy. This ring comes here and then breaks into 2 rings, and then this one comes here. And at the same time, you'll see that this nebula has these ejections. We still don't know what these ejections are from, what create these ejections. This is something that is apparently quadripolar, ejections from the star, so we have no idea about it. But for sure, they're interacting with these rings or with the structures around the star. So first thing is that we have to create so we take the original, so we have HST images from different, taken at different times, more or less around 10 years in separations, and then we do expansion parallaxes in order to measure the expansion of these rings, and we do statistics of the, so we take one of the images and start expanding it angularly in order to try to eliminate the signal, let's say, of the ring. So this is a very, very hard work in which Martin and Gerardo are working very, very hard, and I'm just sitting next to them looking at it. But this is something very impressive. You can actually detect this expansion using HST. Of course, this is a very well-known method for estimated distances and expansion from different nebulae with HST. And some of the things that we actually, when we go into details about these nebulae, is that we see that the rings are actually not rings. They have different structures depending on the angle that we measured emissivity around the star. So this is for the Katsas Nebula, and different angles. So you'll see that the rings are very well defined around this angle, but they're mostly erased in the 50 angle. So making this analysis, we can easily conclude that they're actually not rings. They're things around the inner. Probably a spiral that has been broken. We don't know. So if it was a spiral, it's been erased by the evolution of the star. Because remember, then again, these central stars have this very, very fast wind, this 1,000, 4,000 kilometers per second wind that it gets adiabatically shocked and then produces these hot bubbles that are pressurized. And they're expanding, pushing everything away. At the same time, different processes happen here, instability, so there's a lot of physics that we have to take into account. And then we can create this polar coordinates images. So this is the original image, and that is transformed into R and theta images. In the spiral, you see, the structure is kind of like a straight line with a certain slope. But in the other cases, most of the inner bubble or the jets dominate all the emission. Actually, they do not look like, they look like not even constant lines in the polar angle. So there seems to be disrupted. We cannot follow. This is the most messy one, so we do not follow any structure around. And if we compare the physical size, the actual physical size, taking into account different distances, we see that the spiral, the pure spiral, will be, if this will be like an evolutionary sequence of the distribution of the material, this will be completely erased by the fast wind. Yeah? And so on. But at the same time, you see that there will be more rings extending beyond. So this seems to be kind of like evolutionary sequence. So that's why probably we only have one spiral, because most of the other nebulae have already disrupted this spiral. Part of this project is to try to search for get ALMA observations in order to study the dynamics of these rings. So we want to start from very young protoplanetary nebulae into more evolved and up to planetary nebulae phase. So we were going to try to measure this, the dynamics and the rings. Probably this is kind of like a jet interacting with this ring. So we have to think very carefully about our sample in order to go on with this project. And there are some objects that are very, very interesting. So different jets, arcs, everything. And finally, this is what I've been doing. So we want to test all these physical mechanisms. We want to test what is dominating the destruction of the spiral of the rings. So we performed different simulations by different parameters. So we just defined that the AGB material is more or less uniform constant mass loss rate, but some pulses somehow form around the star. And then we launch different fast winds from different stellar evolution models, from a 1 solar mass star to 2.5 solar mass stars. So at the beginning, all the simulations, they look like this. This is the radial distance, and this is the density, number density, for the two different initial conditions. So what we see is they're more or less r to the -2 density distribution, and then the rings are placed more or less spatially constant distance from the star. And then we launch this fast wind. So we see different things. So this is the top panels are total density, which is ionized plus neutral density, and this is the H-alpha emissivity. So what we see is that the hot bubble, the fast gas, interacts with the AGV material, and then the first thing they do is that thin shell instabilities are formed. These thin shell instabilities form clumps. The clumps trap the ionizing flux. So the ionization of the nebula is not uniform. So we see streaks. These streaks, you more or less can see them here. Some of this. So these are actually real, and we can reproduce those in the simulations. So after some time, the hot bubble increases with size, and you start ionizing more or less uniformly everything. This is for a high density distribution, but for a lower density distribution, these clumps are not so dense, so they do not trap the ionizing flux. So the ionization of the whole nebula is more or less uniform. So we see a ring, and then more or less the rings distributed here. But at some point, the hot bubble eats all these rings. So we're probably mixing all these physical phenomena in order to destroy. If it was a spiral, we can destroy it. This is 4,000 times years, 6,000, 10,000. 10,000 is very old for a planetary nebula, but so far 6,000 we can kind of destroy these rings depending on the density distribution. And these are velocity maps from the simulations. This is the same, the first example and the second example. So this is the less dense. So you see the rings very well. So do not worry about this. This is a numerical barrier. So you can actually ignore this area. You see more or less the rings here. So the nebula keeps evolving, and we see them here more or less. But for the messy case, you see actually that the rings break. And those that are ionized have faster velocity than those that do not have. So this is the way to explain these arcs. So we actually give more momentum because of the photons of the star in this area that is completely photoionized. And as I know, I bore you already, so I just want to give you my remarks. So we did this survey of 700 sources, and we see these structures. We just call them ring-like structures. It could be spiral, rings, arcs, semi-arcs, or ellipses in all kinds of morphological classified planetary nebulae. The occurrence estimate is less than 10%. So we can actually say that if these structures were originally in all planetary nebulae, they have been destroyed by several factors. It is very easy to destroy them. Evolved planetary nebulae do not present any hint of spiral structure, so we only have one so far. No, one in HST, one in SMA, and one in ALMA. There seems to be an evolution of the ring-like features, and this is something that we have to analyze more simulations in order to give definite conclusions, but we think we are on our way there. There are some other mechanisms that can be explored. For example, these are 2D simulations, and there's not a spiral. There are different rings, but it will be easy to start jumping into 3D simulations and launch probably jets or fast wind or producing synthetic observations. Some questions. I think I just said them all, so I'm just going to stop here. Thank you all. Well, in this actually, this one has already been published also in ALMA recently, last year. So this is optical, but it's not because the star is ionizing the material, it's reflected light. So it's dust, and then there are some other ALMA observations of this.
Question. You mentioned that the spiral structures are created probably by binaries. Do you know if this limitation can predict the minimum mass of the to produce these structures? I am thinking, for instance, in planets that around the central star that can create this kind of structure.
No, it has to be kind of like a solar-like mass. And the orbital parameters depend a little bit of, and also, I haven't talked anything about the inclination, but some of these, for example, these might be, because in this case, we're looking at it almost on the plane of the binary, but it could be that those rings are not completely exist because we see kind of like a tilted angle. But it has to be a companion, a massive solar-like companion.
Such a nice talk. As you may know, I'm quite far from your field of research, so maybe I'm asking this stupid. You said that your experiment was handle 700 objects, and then you end up with a small presentation. Could you please elaborate a little bit on how sure you are that your sample includes all objects, or is statistically significant or complete or whatever, in order to have an estimation of the true percentage of such features?
Those 700 sources are the ones observed so far with HST and Spitzer. So,
And include the possible biases?
I don't think so. That's why I presented these statistics. So we see objects from all types. So AGV stars are, most of these AGV data has been taken from submillimeter observations, but the rest of the planetary nebulae and protoplanetary nebulae are taken from HST and Spitzer. These are all objects of this kind observed with HST and Spitzer.
It could be good to have some statistics on different distances beams, so as to see whether the occurrence ratio changes with the distance, with the mean distance to the source.
Yeah, this, I mean, it's not very big.
Thanks a lot for this very nice talk. I think it's very instructive and very, to talk the last one. It is a curiosity. If you suppose that the positive star phase is a factory of dust production, so does the dust play any role in this?
So we think not, because so in the spiral one, for example, IFGL, this ones, for example, this is only molecular emission. This is the star is very cold, so most of this emission is molecular emission because of thermic emissivity. But in the HST images, it's because the gas is being heated up because of this photoionized gas. So they have different origins. So we're using different bands to trace a structure. In some cases, in NGC 3242, we try to compare the optical oxygen-3 image with the Spitzer image in order to see, we were trying to see if, for example, the Spitzer will be behind the optical rings, but we don't have the observations, that we don't have a very nice resolution in order to say it is coming from behind or not, if there's an actual separation between dust and gas. Most of it is photoionized, so central stars of planetary nebulae are very hot.
You just mentioned about the inclination, because I guess if these spiral structures are formed due to a minor interaction, that spiral structure must be on the the orbital plane. So why are all your spirals so round? Because that's very unlikely.
Now, we have some cases. So let's say if you see the complete spiral in the sky, you wouldn't expect, for example, some jets going the other direction, for example, no? Let's say. But we do see that. So you can invoke everything. You can invoke a triple system. You can invoke whatever, a wrapping disk. So you have to take into account that these simulations are this is stellar radii, so 600 stellar radii. So whatever is happening between the two stars has to have some 3 astronomical units within. So they have to be very close or very elliptical orbits, so that the modulation is because of the periastron passage. Inclination things, when you see the complete spiral, it's easy to do. And then you have the spiral, and then you just draw the spiral, and then you can estimate the angle. But in our planetary nebulae, we cannot follow. Actually, we have tried to do we have tried to go with a pencil and then try following from this side into this side, but you cannot follow it. Even though if you think that it's going up, the jets are changing the.
Why don't you see elliptical spirals?
Some of them were elliptical in the 700 source in one of these. Some of them were elliptical.
Elliptical spirals.
Yeah, no.
You don't see any object.
No.
So I don't see the utility of the thing. If the spiral is strong.
For example, this has I don't remember properly, 30.
So that's
30 inclination. And when you keep on doing the inclination, increasing it, sometimes you see some extra. I didn't show it here, but some of this observation, you need some extra structure starts to appear. So that makes no sense if you're looking for spiral. For example, you do not see it here, but I mean, there's it comes something here, and then another one comes from on top of this. So that's because there's some certain inclination, so you see it started from the front and the back. So that makes it more difficult.
So I have a question. Because I guess in the HST you are looking to the ionized gas and CO, much colder gas, and also different densities in the gas. So have you tried to make a map of the densities traveling in one of these structures?
We haven't.
Better than this?
We haven't done much of this. Molecular work has been done previous to us. So we've been doing only the HST so far, HST and Spitzer, and we think it's mostly ionized. It's And those simulations from in 2012, they did a whole group of parameter space. I don't remember how long they went, but they did several parameters simulations, and they create wider spirals.
Ya se comenta about what Pepa just said, because she said that you try higher density band. You plan to make an observation, you can observe simultaneously CO and CO plus, which is a high situation.
Yeah, we have also, I mean, I ignore most of the science in Alma, but Luis Zapata and Alfonso Trejo from HIA, so they're taking into their